In this video, we're going to learn about categorical inferences. These are arguments whose premises and conclusions are categorical propositions. Categorical arguments can be divided by the number of premises they contain. Some of them have only one premise, and this includes two main kinds. One of them is inference from contradictories. The other one is immediate categorical inferences, or ICIs. The other group is formed by categorical syllogisms, which is formed by two premises. So here we're going to focus on immediate categorical inferences and on categorical syllogisms. An immediate categorical inference, or ICI, is an argument that is characterized by two things. One is that they have only one premise, and second, that both the premise and the conclusion belong to one of the basic categorical forms, namely A, E, I, or O. One of the most common type of ICIs is conversion. This is obtained by taking any categorical proposition and using it as a premise. And the conclusion is going to be the same as a premise, but with one big difference. The predicate and subject terms are going to be switched. The premise and the conclusion are going to be said to be converses of each other. Here are the conversion forms for each of the categorical propositions. So with A propositions, we have using as a premise all S are P, then the conclusion would be all P are S. And if you take form I, you have as the premise some S is P, and the conclusion would be some P is S. Now, you may have noticed that some of these forms are valid, but not all of them are. We can use Venn diagrams to determine which of these forms are valid. So let's begin with I. Is conversion valid for I? Let's do the Venn diagram for it. I is of the general form some S is P. So what we're saying here in the Venn diagram is that there is at least one individual that is both S and P, right? That's why we add an asterisk in area 2. The converse of some S is P is some P is S. And the Venn diagram is exactly the same. We're saying that there is at least one individual that is both P and S, right? And again, here we're putting an asterisk on area 2. So we can see that both I and its converse are true in exactly the same circumstances. So whenever I is true, then its converse is going to be true as well. But this fits the definition of validity. Whenever the premise is true, the conclusion will be true as well. So conversion for I is indeed valid. Let's give a more concrete example. The premise is of the I form. Some cats are pompous. And we have the diagram for that below the proposition. And the conclusion is going to be its converse, namely some pompous things are cats. And we also have the diagram. So we can clearly see that it's impossible to make one true without making two true as well. So an argument from 1 to 2 will be valid because it is impossible to make the premise true without the conclusion being true as well. In fact, these two sentences are equivalent, right? They say the same thing because exactly the same diagram conveys what both of them say, right? So we have the same information, namely that the intersection of S and P is not empty. That means that the inference from our sentence 2 to sentence 1 above is also going to be valid. So we just saw that conversion for I is valid. Now what about A? A propositions are of the form all S are P. And the Venn diagram is formed by shading area 1. That is, shading the part of S that doesn't overlap with P. And so what we're saying is that there isn't even one S, right, that isn't also P. All the S's that we find are also going to be P. A proposition of form A is all cats are pompous. And here you have the diagram in which, again, we shade area 1, which means that area 1 is empty. Now, its converse is all pompous things are cats. And its Venn diagram is formed by shading area 3. That is, saying that area 3 is empty, namely that there isn't one P that isn't also S. So notice that the diagrams for the conclusion and for the premise are different, right? So they convey different information. And in particular, the diagram for the conclusion contains information that is not present in the premise. An example situation would be the following. Suppose that there are only 3 things in the world, Al, Beth, and Claire. And suppose that all of them, the 3 of them, are pompous. Now, Al and Beth are cats, but Claire is a giraffe, for instance. Now, the situation is accurately depicted by the diagram to the left. Let's take the cats. So let's take the first cat, Al. Is it pompous? Yes. Let's take the second cat, Beth. Is she pompous? Yes. So, and we're done. So the area of cats that are not pompous is empty. So our example makes P true. However, it doesn't make C true. This is because there is at least one pompous thing that isn't a cat, namely Claire the giraffe. So area 3 wouldn't be empty because Claire would be located there. So this example shows that it's possible to make all cats are pompous without making its converse true as well. And in general, it is possible to make any proposition of the form A true without making its converse true as well. This means that conversion for A is not valid. And this is made evident by the fact that the Venn diagrams for A and by its converse are different, and thus convey different information. And in particular, the diagram for the conclusion contains information that is not included in the diagram for the premise. So far we have that conversion for I is valid, but conversion for A is invalid. What about the 2 remaining forms, E and O? Let's deal with E first. So E is a proposition of the form no S is P, and its converse is no P is S. We already know that the diagram for E is obtained by shading area 2. That is that S and P have no members in common. So the diagram for no cats are pompous basically would say that the area that contains things that are both cats and pompous is going to be empty. But notice that this diagram also makes the converse true, that is, no P is S. This means that an E proposition and its converse basically express the same information, namely that the intersection between the classes of the 2 categorical terms are empty. So we can use the same diagram to represent the proposition that no cats are pompous as we use for representing the proposition that no pompous things are cats. Both would be saying that the class of things that are both cats and pompous is empty. So conversion for E is valid. So far we have 2 valid conversion patterns, namely those for I and those for E. Finally, let's deal with O. Again, an O proposition is one of the form some S is not P. It is represented by placing an asterisk on area 1. That is, there is at least one individual that is located in the area of S that is outside of P. So suppose that the proposition is some cat is not pompous, or some cats are not pompous. Again, the number doesn't matter, right? And so that dot, for instance, would represent Bob, the non-pompous cat, right? So Bob is inside the circle of cats, but outside the circle of pompous things. Now let's change the example a little bit because I'm a bit tired of pompous. Suppose that our example is some cats are not humble. And so proposition 1 is done by placing an asterisk in area 1. And that area 1, and that asterisk there, represents a Terry, the non-humble cat. The converse for this sentence is some humble things are not cats. And notice that the diagram is different. And this illustrates the fact that you can make one true without making two true as well. So here's a summary of our results so far. Conversion for A is not valid. Conversion for E and I is valid. And conversion for O is not valid.